The battery pack is no longer a part. It is the car. For more than a decade, America was told the future of the electric vehicle had already been solved. Put the battery under the floor bolt, the body on top, add better software, and wait for chemistry to improve. That was the skateboard platform, the architecture that made Tesla famous and forced Detroit to rebuild its entire EV strategy around a flat, heavy armored battery box. But that assumption is now being attacked at the structural level. China's latest cell-to-chassis architecture does not simply improve the battery pack. It begins by questioning why the battery pack should exist at all. Instead of treating cells as cargo sealed inside a metal container, engineers are turning the battery itself into the load-bearing floor, the crash structure, the thermal system, and the spine of the vehicle. That changes the rules. Weight that used to sit beneath the car as dead mass is now being used as structural strength. The floor that once flexed under stress is becoming a bonded energy matrix. And the old EV platform, the one Western automaker spent billions trying to perfect, suddenly looks like a transitional technology. This is not a software gap. This is not a range trick. This is a hardware revolution underneath the passenger cabin. And if Detroit still sees the battery as a box bolted below the vehicle, it may be fighting the next EV war with the architecture of yesterday. The skateboard platform became the new legacy trap. The irony is that the skateboard platform was once treated as the great liberation of the electric age. Compared with combustion vehicles, it seemed brutally logical. Remove the engine bay, remove the transmission tunnel, push the battery into the floor, lower the center of gravity, free up cabin space, give designers a flat foundation, and let software finish the job. For a while, that logic worked. Tesla proved that a heavy battery pack could become a performance advantage if it was placed low enough. Ford, GM, Rivian, and nearly every serious EV program followed the same basic principle. Build a protected battery enclosure, make it strong enough to survive impact, then bolt the body and suspension systems around it. The result was simple to explain, easy to scale, and familiar enough for traditional factories to understand. But from an engineering standpoint, this also created a hidden problem. The battery pack became a separate object inside the vehicle's architecture. It needed its own casing, its own brackets, its own sealing system, its own crash protection, and its own service logic. That meant hundreds of pounds of aluminum steel bolts and wiring that did not move the car forward. They existed only to protect and carry the cells. That is parasitic mass. Cell-to-module architecture made this worse by stacking complexity inside complexity. Cell-to-pack improved the equation by removing the intermediate modules, but it still kept the same basic idea. The battery was a sealed box underneath the car. Cell-to-chassis breaks that idea apart. Instead of asking how to build a better battery box, it asks why the box is there in the first place. And that is where the Western EV playbook starts to look uncomfortable. Because if the pack enclosure is dead weight, then every automaker still designing around it is not merely behind on chemistry. They are behind on structure. From battery cargo to structural spine, the real violence of cell-to-chassis engineering begins when the battery stops being a protected passenger and becomes part of the vehicle's skeleton. In a traditional EV, the pack is a sealed unit hanging below the cabin. In a true CTC layout, that separation is removed. The upper cover of the battery enclosure disappears, and the cabin floor itself becomes the top boundary of the battery structure. That sounds simple. It is not. It means the floor beneath the seats is no longer just stamped metal designed to carry people and interior trim. It becomes a structural lid for an energy matrix. The cells are bonded directly into the longitudinal rails and transverse beams of the vehicle using high-strength structural adhesives similar in purpose to what aerospace engineers use when they need lightness and rigidity at the same time. The battery is no longer being carried by the chassis. The battery is helping carry the chassis. This is why the shift is so dangerous for legacy automakers. Detroit knows how to build frames, subframes, floor pans, and crash structures. Tesla knows how to package batteries efficiently. But CTC fuses those worlds together until the old categories begin to vanish. For an American driver, the result is not just a cleaner engineering diagram. It can mean more usable battery capacity in the same footprint, less redundant metal lower vehicle mass, and a floor structure that contributes directly to stiffness instead of merely occupying space. That is the industrial threat. The disruptor is not adding one clever component. It is deleting an entire layer of the vehicle and forcing the remaining structure to do more work than before. Torsional rigidity becomes the new weapon. The next battlefield is rigidity. Not horsepower, not screen size, not another software update. Rigidity. In a normal vehicle, the chassis is never perfectly still. When one wheel climbs a steep driveway in a Texas suburb, while the opposite corner stays low, the body twists. When an SUV changes lanes hard on a Colorado mountain highway, the frame flexes. When a heavy EV hits broken winter pavement in Michigan, the suspension is not the only system taking punishment. The structure itself is being loaded unevenly. That twisting matters because suspension only works correctly when its mounting points stay where engineers intended them to be. If the body flexes, the geometry changes. The tire contact patch becomes less predictable. Steering precision fades. The vehicle may still feel safe, but underneath the chassis is negotiating with physics instead of commanding it. Cell to chassis changes that relationship. When thousands of tightly packed cells are bonded into the floor pan and structural rails, they begin to act like the core of an aerospace honeycomb panel. In an aircraft wing, the core material is not empty filler. It resists shear, prevents buckling, and allows the outer skin to behave like one rigid surface. CTC applies the same logic to the bottom of an electric vehicle. The floor stops behaving like a flexible sheet. It becomes a dense bonded load-bearing block. That is how some advanced EV platforms are pushing torsional rigidity into the range of roughly 40,000 to 45,000 Newton meters per degree. To understand why that number matters, a conventional combustion sedan may sit around half that figure. In plain language, the CTC vehicle resists twisting with a level of stiffness once associated with exotic performance structures, not ordinary family EVs. And this is where the threat becomes practical. A stiffer structure allows the dampers, control arms, and tires to do their jobs without the body adding noise into the system. The driver feels cleaner steering. The chassis stays calmer under load. The vehicle carries battery weight not as a penalty, but as part of the reason the platform feels planted. That is the inversion Detroit must study carefully. In the old EV equation, the battery was heavy mass you had to manage. In the new equation, that same mass becomes the weapon that makes the machine harder to bend. Crash physics are being rewritten. Rigidity is only the first consequence. The deeper disruption is crash physics. In a traditional EV, the battery pack is the component everyone is trying to protect. During a severe side impact, the rocker panels cross members' floor rails, and B-pillar must absorb the violence before it reaches the cabin, and before it reaches the battery enclosure. That pack may be armored, but it is still a chemical box filled with stored energy. If the structure around it fails, the battery becomes the liability. That is why conventional EV safety is built around separation. Keep the battery sealed, keep it away from intrusion, build a protective cage around it. Add mass, add metal, add layers. Cell to chassis reverses the logic. Because the cells are bonded into the floor structure, the battery matrix itself becomes part of the crash pathway. A side impact no longer strikes only a hollow rail or a limited crumple zone. The force can be distributed across the bonded cell array through structural adhesive crossmembers and the wider floor architecture. Think of each cell not only as an energy container, but as a tiny structural column. One cell alone does not stop a collision. Thousands of cells bonded together inside a rigid matrix change how force moves through the vehicle. Instead of concentrating violence at one impact point, the architecture spreads that violence across a wider and denser structural field. That is the real breakthrough. The chemistry that once had to be protected from the crash is now being used to help resist the crash. The battery stops being only a fire risk under the floor and becomes part of the shield, between the impact and the people inside. For American drivers, this matters in the scenarios that do not appear in glossy product videos. A pickup running a red light into the side of an EV in Phoenix, a winter collision on a Michigan highway, a heavy SUV sliding across an intersection in Chicago. In those moments, the question is not whether the car has more range. The question is how quickly the structure can root violence away from the cabin. And CTC suggests a brutal answer: the safest battery may not be the one hidden inside the strongest box. It may be the one that becomes the strongest part of the vehicle itself. The thermal paradox under the passenger cabin. But this is where the brilliance of cell-to-chassis turns into a frightening engineering bargain. If the battery is now the floor, then the most powerful chemical system in the vehicle is no longer sitting inside a separate armored box beneath the cabin. It is integrated directly into the structure under the passenger's feet. That creates the thermal paradox. A lithium battery failure is not a normal mechanical problem. When thermal runaway begins, heat can rise toward extreme temperatures sometimes discussed around the 800 degrees Celsius range in severe cell failure scenarios. In an old-style battery pack, the enclosure at least acts like a physical barrier. It gives engineers another layer between the fire event and the cabin. CTC removes much of that separation, so the entire thermal management system has to become more aggressive, more integrated, and far less tolerant of error. Cooling cannot simply be a plate attached beneath modules, hoping to pull heat downward. In advanced CTC thinking, the chassis itself becomes part of the cooling network. The structural beams that create rigidity can also become hollow pathways for dielectric cooling fluid. The same cross members that help stop the vehicle from twisting can route heat away from tightly packed cell arrays. In other words, the skeleton of the vehicle becomes a radiator. Then comes the second layer: propagation control. If one cell fails, the danger is not only that cell. The danger is the chain reaction. That is why insulation materials such as aerogel become strategically important between cells. Their job is not glamorous. Their job is to slow or block heat from jumping sideways through the battery matrix, like fire moving through dry grass. This is the trade-off America must understand. CTC can make the vehicle lighter, stiffer, and more space efficient, but it also concentrates engineering responsibility into the floor of the car. Thermal routing, cooling channels, insulation barriers, sensor logic, and emergency shutdown systems all have to work as one organism. In Phoenix summer heat, during repeated fast charging, or after years of thermal cycling through Michigan winters, this is not a theoretical concern. It is the price of turning the battery from a protected component into a structural organ. The technology is powerful, but the margin for sloppy engineering disappears. Repairability and the insurance shock. Now comes the part that no marketing department wants to put on a launch poster. Cell-to-chassis may be brilliant for stiffness, packaging, manufacturing speed, and weight reduction, but it also attacks one of the oldest assumptions in the American car market: that a vehicle can be repaired, rebuilt, resold, and kept alive long after the first owner is gone. A traditional EV battery pack may be heavy and inefficient, but it is at least a separate service object. In theory, a damaged pack can be dropped from the bottom of the vehicle. A module can be diagnosed. A casing can be inspected. A technician has a physical boundary between the battery and the rest of the car. CTC destroys that boundary. Once the cells are glued, bonded, sealed, and structurally integrated into the floor, the battery is no longer something you remove from the chassis. It is part of the chassis. If a severe crash bends the floor structure, the battery matrix may be compromised. If a deep internal cell cluster fails beyond recovery, the vehicle structure itself may become economically useless. That is the nightmare for collision centers and insurers. A crash that once meant frame repair, battery inspection, and component replacement may now become a total structural and chemical write-off. The car is not simply damaged. Its skeleton and energy system may have been injured at the same time. For American buyers, that changes the ownership equation. Insurance premiums could become more sensitive to structural battery damage. Used EV values could depend heavily on whether inspectors can verify the hidden condition of the bonded cell matrix. Independent repair shops may find themselves locked out of the most important part of the vehicle, not because of software, but because the component is physically fused into the body. And this is exactly why many legacy automakers have been cautious. The American auto ecosystem is not just factories. It is dealers' body shops, insurers, auction networks, used car buyers, warranty systems, and repair technicians. CTC does not just redesign the car. It threatens to redesign the entire life cycle around it. China appears willing to accept that gamble. The calculation is brutal. Gain more battery capacity in the same footprint, remove redundant parts, cut mass, simplify assembly, increase rigidity and trust, active safety systems to make severe structural crashes rare enough. That may be rational, but it is also a line in the sand. Because once the battery becomes the body, the automobile starts to behave less like a repairable machine and more like a sealed industrial device. The bolted battery pack era is over. This is the moment Detroit cannot afford to misunderstand. Cell-to-chassis is not just another EV packaging trick. It is a declaration that the old electric vehicle architecture, the heavy battery box, the separate chassis, the redundant armor, the bolted-on energy system, is being pushed toward extinction. The advantage is not coming from one headline number. It comes from the accumulation of structural gains, more usable capacity in the same footprint, fewer wasted parts, lower mass, higher torsional rigidity, cleaner manufacturing flow, and a vehicle floor that no longer just supports the cabin, but actively defines the machine. That is why this matters beyond China. If this architecture scales, the next generation of EVs will not be judged only by range horsepower or screen technology. They will be judged by how completely the battery has been absorbed into the vehicle's physical identity. The winners will not simply build better packs. They will delete the pack as a separate idea. For Ford, GM, Tesla, and every automaker still tied to the skateboard logic, the warning is clear. The future EV may not be a car powered by a battery. It may be a battery engineered into the shape of a car. And once that becomes the industry standard, the companies still bolting dead weight under the floor will not look cautious. They will look late. The era of the battery pack is ending. The era of the structural battery has begun.